All right, in this lesson, we are going to put our calculus to really good use to get some very quick results that otherwise would not be possible for us. So we know we have our empirical results. So we do not prove this. We simply write this down as the equation that describes simple harmonic motion, the block oscillator. And if we start at time t equals 0, that will correspond to no phase shift. So phi equals 0. The phase shift always refers to the starting point. So at time t equals 0, the only thing you have left in the phase is the shift term. So, for example, if the phase shift were positive 90 degrees, pi on 2, that would mean we actually picked up the oscillation here at this point. So we started our stopwatch at 90 degree point where the block oscillator itself was released from the right and would be passing through the 0 point going towards the left. So the phase shift just tells us where we started, and that's why I was saying you always start at the beginning. Let the cosine function have no phase shift. Start your analysis by pulling the block to the right and releasing it from rest at this position, unless the problem is forcing you to do otherwise. Okay, well, let's put our calculus to good use here. So we're going to take the derivative of the position function to get the velocity function. So we're taking the derivative of cosine theta, which equals negative sine theta d theta dt. And we'll see how that plays out numerically. But basically, what we need to keep in mind is that we need to take the derivative of theta and stick it on the end. So if you've had calculus, you know exactly what I'm talking about here. And again, we'll be doing this numerically in our homework as well. Well, when we do this to our function, right? So we have a cosine omega t plus phi equals negative sine theta. So that's why we get the negative sine theta. But then we need to take d theta dt. So d theta dt gives us another omega out here on the end. So I'm going to bracket, and I ask you to please bracket the omega a together, because whatever sits out in front of the sine or cosine function is the amplitude of that function. So omega a is the amplitude of the velocity function, and that will be the maximum velocity that our block oscillator will have. So it's a negative sine function. So the velocity, the particle starts from the block on the end of the spring, starts from rest. It picks up speed, and remember we said at 90 degrees, it's passing through the origin and has its maximum speed going backwards. So wow, look at this. Calculus works. And we have another equation. We have that Vmax equals omega a. So my advice in terms of memorization is to always memorize the position function and generate the velocity function. If you need it, trying to continually memorize equation after equation after equation, I think gets too cumbersome. Well, let's continue to put our calculus to good use. The derivative of the sine function is positive cosine theta d theta dt. So now we're taking the derivative of our velocity equation, so the acceleration, right, equals dv dt. So you maybe want to add that in there to remind yourself of that. So acceleration equals dv dt. The derivative of sine is cosine. Now the negative we don't introduce with the derivative. The negative is already there, right? So the negative is already up here, and that's this negative here. But cosine, derivative of cosine theta, d theta, so we pull out the derivative of omega t is omega, so we get another omega out front. We're going to bracket that together. Whatever sits out in front of the sine or cosine is the amplitude. So our acceleration is given based on having a maximum value of omega squared a, and let's see if it makes sense to have a negative cosine function, because at time t equals 0, we have a maximum acceleration backwards. And that absolutely makes sense from the spring. The spring has its maximum force when it's pulled the furthest to the right. So it's got its maximum acceleration at F max, which is minus K amplitude, right? So we'll have our maximum acceleration, and if we look at our acceleration function, boy, the math falls together nicely. We have an A cosine omega t plus phi embedded in there. We have a cosine omega t plus phi and an A, so let me zoom back in now. So A cosine omega t, right, equals x. So the acceleration is directly proportional to the position, but we knew that because the force is Hooke's law. F equals minus kx. So I know, wow, there's a lot going on here, but if you are proficient with your calculus and you remember the amplitude of the trig functions and remember what they are, you'll be able to very quickly start from our initial equation, x equals a cosine omega t, which absolutely you need to have memorized and be able to quickly generate the others by taking the derivatives. So I'm going to again leave this so you can pause the video and make sure that you do not miss your annotations here. And we are going to do more with this in the notes and more homework problems to get a better feeling for all of this as well.